So the sketching of these graphs is going to get slightly more complicated, and we're going to try and figure out how we can do it with our calculators as well. But I wanted to investigate a particular graph because it's going to illustrate a number of different points about the Edexcel specification. So I've written at the top for the important note that it's usually possible to have negative r, where we'd end up on the opposite side of the origin. So I don't know, let's say you were talking about an angle of pi over 4, which is over here. If you had a negative value of r, it would actually end up as somewhere on the opposite side of where it would be. But for Core Pure Year 2, in Edexcel, we assume that we only sketch the parts of the curves where r is greater than or equal to 0. And that's kind of the annoying thing, is when you use your graphics calculators or when you use Desmos, it won't do that. It will plot everything with positive r and negative r. But Edexcel will remove anything that has got negative r. So actually this diagram that I've got drawn here is like a polar rose, because it looks like a flower and it's polar equations here. I've tried to represent the parts that are positive and the parts that are negative, and how we can kind of break that down to figure out what's going on here. So the bits that I've marked in as red are where r is positive. So this is where r is positive, or greater than or equal to 0. And then the black dotted lines that I've got here are where r is less than, or I guess equal to 0 as well. I should suppose it's just really when it's less than 0. And we want to figure out why these certain like petals, and they literally would call these bits petals. The language is often based around roses and flowers because they just seem to look like those things that come up in nature. We want to see why certain bits are negative and how we could actually think about what the sketch would look like if we removed those negative sections that we've got there. So this diagram that I've got here is r equals sine of 4 theta, and we want to make sure that r is greater than or equal to 0. So I've said if r is greater than or equal to 0, then 4 theta must be between 0 and pi. Why am I saying it needs to be between 0 and pi for it to be greater than or equal to 0? Yeah, if you think about what the sine graph looks like, the sine graph is positive between 0 and pi. If this section in here was between pi and 2 pi, then the value of r would be negative because it's from the negative section. So it's going to be positive if it's between 0 and pi, or it's going to be positive if 4 theta is between what and what? When else is it going to be positive? Between 2 pi and 3 pi, because you can just add 2 pi onto both of those things. Or between what and what? 4 pi and 5 pi. Or 6 pi and 7 pi. And you could obviously say also between 8 pi and blah, blah, blah. But why do you think I'm not going to go to 8 pi and I'm going to stop at this stage? Because it's going to be repeating. Because if you look at what's happening here, these are all 4 theta. Eventually I'm going to want to divide them to find out what theta is going to be between. So if I had it was between 8 pi and 9 pi, it's going to go bigger than 2 pi. And remember, we're only just interested in how it looks like around this particular one. Okay, so that's why I'm just going to be looking at these 4 different situations that we've got here. So it's going to be positive between 0 and pi, but there's a 4 theta in the middle. So theta, let's first of all investigate this first one. I don't know why the board is behaving so badly. Theta is going to be between 0 and pi over 4. I'm not going to do it for every single one of these here. I've just divided both of the parts of the inequality by 4. And now what I'm going to do is I'm going to draw a table to help me reason with what's happening here. So I'm going to have my value of theta and then my value of r. And so I'm going to do theta. In between, I'm just going to do an in-between value, in between 0 and pi over 4, pi over 8, and I'm also going to put in pi over 4 into here. So when I put the sine of 0, I would just get 0. Now I'm going to do the sine of 4 times pi over 8, which is the sine of, which is? Sine of pi over 2 is 1. And then the sine of 4 times pi over 4 is the sine of pi, which is 0. So look what's happening in the graph, okay? For this first bit that we've got here, this angle that I have here is pi over 8. It's not exactly easy to see that, but if this is pi over 2 and this is pi over 4, then this one here must be pi over 8 because it's halfway around. And you can see that when the angle is 0, the length of the line is 0. When the angle has moved to pi over 8, the length of this line here, and I'm not going to draw this on everywhere, the length of this line is 1. And then when it goes to pi over 4, it goes back to 0 again.
So the greatest will be from, the greatest length is 1.
The greatest length is 1, and you can see that on my Desmos version of it here, that I've got the polar coordinates with this kind of radial coordinates, or radial grid. So you can see it's going to go from 0 to 1, back to 0. And then we'll just briefly look at what the other ones are going to be as well. So this next one that I've got here, which is the 2 pi one, well, if I divide all of this by 4, I would have pi over 2 theta to 3 pi over 4. And so that section that I've got here is where r is going to be positive. I'm not going to do a table of values for this, but we know it's going to go 0 and 0 at the pi over 2 and 3 pi over 4. There's pi over 2 here. There's 3 pi over 4 here. And in between that section, we've got that petal doing that loop. Okay? So this first section, and this might get a bit busy, so I wouldn't necessarily advise drawing all of this on your graph. This green section was talking between 0 and pi over 4, and it did this little loop like this. So you can clearly see how the next section and the section after is going to then correspond to this red petal and this red petal that we have here. And then the other parts are going to be corresponding to the negative sections. So I'm just going to have a look at one of the negative sections, and I'm going to think about the first negative section. So let's just consider the fact that if r is less than 0, then what can you tell me about 4 theta? What would it be in between for it to be less than 0, or less than or equal to 0, I guess? When is sine theta less than 0? Between pi and 2 pi. So we're just going to investigate this first one. In other words, you've got pi over 4 and pi over 2. Try and make a prediction to yourself. Which of those dotted line petals is it talking about between pi over 4 and pi over 2? Is it this petal here, which I'm going to call number 1, this petal which is number 2, this petal number 3, or this petal number 4? Which one do you think it's referring to? Which one is the negative one going to be?
3.
Why do you think it's going to be 3?
Because you said something about when there's a negative value, like flip it.
Yeah. So in this range that we've got here, the values of r would go 0, minus 1, 0. So you're tempted to think it's number 1, but it's not number 1 because it's going to go 0. Instead of going up to 1, it's going to go 0, minus 1, and then back to 0. Okay, so the dotted line petals will not appear in the Edexcel specification. What we actually would have would just be the ones with the red lines. Pardon?
Pi over 2 is up there.
So it's in between pi over 4 and pi over 2. So this is where my diagram's going to get a bit busy. I'm talking about this section, which is pi over 2, and this section, which is pi over 4. So it looks like I'm talking about that petal, but actually, because it's going into the opposite direction, because it's going into the negative direction, we're actually meaning it's going backwards over here, which is why they don't include it in the Edexcel specification. If r becomes negative, pardon? From the center, it's negative from the center. If we're talking about this angle over here, which is halfway between pi over 4 and pi over 2, which is 3 pi over 8. Yeah, 3 pi over 8. If you have minus 1, we're not talking about up here. We're actually talking about minus 1 in the opposite direction of that angle. So the main thing I'm trying to illustrate with this example is that there will be sections that are missing. And the missing section that I'm talking about with this bit, which I'll highlight in this kind of purpley colour, is actually corresponding to this dotted one that we have down here that won't be there. So the overall pattern that you should have for this one when you think about what it looks like is you have a petal between those bits. You then have a petal between those bits, a petal here, and a petal here. And again, you've got this kind of, there's like missing petals. That one's not been drawn very well. That one should be a bit more like this. So you've got like a missing petal here, 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 and here. That's what it should look like on the Edexcel specification. This is what it looks like on Desmos. And I had to break it down and do all of those sections with the separate regions. No, Desmos won't do dotted lines and solid lines. Desmos will make it look like a full flower with 8 petals. I had to go through, I plotted each of these petals individually. In fact, I'll show you because it will tell you more about what's going on here. I plotted each of these petals individually. So you can see all of these bits have all got sine 4 theta as the description, and I've got all of the different ranges. And so when I've done it in black and dotted line, I knew that R was going to be negative in that particular section because I knew how the sine graph behaved. And you can just see I've got all 8 of those petals there, which corresponds to the ones I wanted to highlight as being positive petals and the ones I wanted to highlight as being negative petals. So this is a word of warning. If you use Desmos when you're practicing at home, it will show you the negative bits of R. If you use your graphics calculator, it will show you the negative bits of R. You need to decide which are the bits that you're going to be inputting for your values of theta to think about what it might look like. So the graphics calculator is good, but there's a little bit of a thing that's holding us back with how these graphs are actually going to end up looking. So I don't know how much detail I'm going to go into this next one, but we have a similar kind of thing that we've got in this case. We've got r squared equals a squared cos 3 theta. And again, we've got some of the petals that look like they are positive and some of the petals that look like they're going to be negative ones in here. So r squared equals a squared cos 3 theta. This one I don't think you can even type in Desmos because they don't like starting with r squared. And also in your graphics calculator, you can't start it with r squared either. So the way I think I did this one is I think I put in r equals a cos 3 theta to the power of a half. And I typed in r equals minus a cos 3 theta to the power of a half. So I square rooted both sides and I put in the positives and negatives. But this section that I have here, which is the positive section, are the red ones. It's this bit, and this bit. The negative bits wouldn't appear there. And I guess the fact that I've got r squared here, this is actually already restricting that r needs to be positive, because if it's r squared, it's been squared, so it's positive. So technically, these dotted lines only have appeared because I wrote it in this form. So let's just write down what that is. Because it is r squared equals, this is already saying that r should be positive.
You see the yellow r equals a cos 3 theta to the half.
Yeah.
Couldn't that also give negative values of r? If you had like a input of theta which gave cos as negative.
If you then have cos as negative, you would then get a square root of a negative, which would then go to an imaginary rather than a negative. And then imaginaries, I have no idea how we would be plotting those on polar coordinates just yet. So again, I'm not expecting you to suddenly like see this and be like, I'm an expert. I'm just expecting you to look at these ideas and think to yourself, okay, I think I can start to see a little bit about what's going on here. I think I can start to see some of the things that are going on. So we've got some negative petals and we've got some positive petals here. The positive petals are the ones that we want to be thinking about. What we'll eventually be doing is trying to find out the area like inside one of the petals. If you wanted to find out the area of the whole diagram, well, you would just find out the area of one of the petals and triple it, because it's clearly a symmetrical diagram. So you need to use all your knowledge of functions here to think symmetry. You know, how do all these things connect together? Don't just do things the long way. Try and be like puzzle solvers, because this is a topic that's kind of being like put right on top of everything else we know. So it is going to be based on all of the other topics that we've been studying as well.
Corresponding to that, the coefficient of theta.
Yeah, it's going to correspond to the number of in front of theta. So you see on this one it was 4 theta. There were 4 positive petals. 3 theta, 3 positive petals. So it's just really to kind of give us a bit of a hint about how some of these things work here. Now this one, I've got r equals sine 3 theta. And what have you noticed is happening in r equals sine 3 theta with the positives and negatives? Yeah, the positive petals are in the same places where the negative petals would be. So let's just think about the background of where this comes from. If r is greater than or equal to 0, what can you tell me about 3 theta that we said before? What would it be for it to be positive?
Between 0 and pi.
It's between 0 and pi for the sine graph. So it's between 0 and pi over 3. And we actually know that when theta is halfway between 0 and pi over 3, which is pi over 6, r would be equal to 1, its maximum value. So here is 0. Here is pi over 3. Here is pi over 6, where it's at that maximum value at that particular point that you've got there. So you've got that petal in between 0 and pi over 3. Now let's just consider one of the negative bits. So the most obvious negative bit, if r was less than or equal to 0, is when 3 theta is in between pi and 2 pi, which is going to be pi over 3 and 2 pi over 3. So pi over 3 and 2 pi over 3 is in between. Let's do this in an orange colour. Here is pi over 3. Here is 2 pi over 3. So the negative petal that it's talking about is this one that is down here, which happens to overlap with one of the positive petals that we have later on. So it's just a word of warning. There's nothing, I can't really see them asking a specific question about this, but I wanted to show you this to develop your understanding of what is going on with the graphs. Not because I expect you to memorize this stuff, but just to reason to yourself, okay, well, I can restrict some of these values to try and predict what these might look like. And to warn you that when you use Desmos or you use your graphics calculator, you are possibly going to be ending up with something that is not the true graph, okay? So what other bits did I want to show you here? Okay, so we've looked at those three, which I enjoyed making on Desmos. Just wanted to show you some of the kind of other graphs that you might come across with this as well. So I found this on Wikipedia, and these are different Rose curves that you can get. And these Rose curves that all come from polar coordinates, these ones are an example. They are all r equals cos of k theta. And actually, I suppose we could rewrite that with the extra information they've given us. These are all r equals cos of n over d theta. And running along the top here is the n values. And then running down here are the d values. So if you did the cos of, I don't know, let's say like 4 over 3 theta, 4 over 3 theta, I believe, should give you this particular one here, if I've got the rows and stuff correct. It's just kind of interesting to see like the crazy kinds of patterns. There was a toy in the like 80s that I had when I was growing up called Spirograph. Did you ever have a Spirograph? Where you'd put the pen in the thing and you follow it around? Yeah. And they make these kinds of things here. So I wonder who made the Spirograph. I wonder if they were further mathematicians who had done maths at university and sort of saw these patterns. So you get these weird kind of patterns, and I actually spot one of these I have seen in the exam. I think I've seen this one come up in the exam before. And I think some of these other ones we've just been sort of talking about. You can see the kind of more floral looking kinds of ones that we've got there, okay? And you can end up with some pretty wild looking ones. So here this is theta cos of 3 over 2 theta. And I don't know if you remember from before, but do you remember when we have r equals theta? R equals theta was a spiral. And then we've got this bit here, which is a rose. So we've got theta, which is the spiral, cos of something, which gives you a rose. And combined together, it's actually a rose that is spiraling out and gives this like super crazy looking pattern that we've got here. Pretty cool, right? And you're just going to experiment with different things on your graphics calculators on Desmos, but you're also going to be aware of the fact if it goes to negative, it's not part of the edXL spec. So it may look different to the diagrams you see in Solution Bank or in exam papers as well.
The range be like?
So this range has stopped. I can't remember what this range went up to, but this looks like we can probably figure out, it looks like it's, if that's 150, 160, 170, 180, 190, we can just do 190 divided by pi. So that the range is probably 190, and that's how many pi?
60.47.
So like 60 and a half pi is what that range is. And obviously you could do that range forever, but then it's just going to get a bigger and bigger diagram. And again, the range will usually be specified in the question for ones that are like this. These ones, I don't really care what the range is because it's going to do this pattern indefinitely. It's just going to always be tracing over itself. And I think there's one of them, I can't remember it. I'm not going to talk about it now because I'll get myself confused. But they basically have these really cool patterns that we have here, okay?